Hello everyone, welcome to all of you in my YouTube channel. So in this particular lecture, I am going to discuss about the Laplace transform and some of its properties. So the Laplace transform means suppose we have any function. Suppose we have any function f of t, then the Laplace transform of the function f of t is defined as f of s is equal to 0 to infinity e to the power minus st f of t dt. Okay. Mm, and in for all the positive values of the t, integral should exist. The Laplace transform is represented as f of s. Okay, f of s actually it is the Laplace transform of the this function f of t. Okay, we have the function of t, and its Laplace transform L of f t. It is also represented by f of s, and it is given by 0 to infinity e to the power minus st f of t dt. Okay, so let me going to discuss. This is the basic fundamental formula for finding the Laplace transform of any function. So now I'm going to discuss the linearity of the Laplace transform. It actually Laplace transform follows the linear property. Linear property means suppose we have any two function f of t and g of t. Okay, whose we know whose linear f of t and g of t are the the two function whose transform exist, and let us suppose that f and a and b are any constants. Then the Laplace transform of a f of t plus b g of t is equal to we can actually distribute this Laplace transform into the both function. So a Laplace transform f of t plus b Laplace sorry so here this is Laplace transform of gt. Okay, so needs little bit correction over here. Okay, so this is the correction needed over here. Now and now using the formula, the Laplace transform of a f of t plus b g of t means for this particular case, we have the function, we have to treat this whole as a function. Then by the formula of the Laplace transform, we know that 0 to infinity e to the power minus st f of t dt. So in this case, in this case we have the function a f of t plus b g of t. That's why we can now actually we can multiply, we can divide, we can make the parts of the integration to both the terms. By doing so, in doing so, e to the power minus st f of t, a can be taken outside, and similarly for this as b is constant, so we can write e to the power minus st g of t. So this is, if we look carefully, 0 to infinity e to the power minus st f of t dt, it's also be the Laplace transform of f of t, and this is the 0 to infinity e to the power minus st g of t represents the Laplace transform of gt. So it implies that the Laplace transform obeys the linearity property, and this is the basic condition. This is the property that we have to show. Now let us discuss another topic, and that is the change of scale property. Okay, change of scale property. So according to this property, it says that if we have the Laplace transform of f of at, okay, we have any function f of at, the Laplace transform of f of at will be is equal to 1 by 1 divided by a, and Laplace transform of s divided by a. Okay, this is the property. So this f of s means actually the Laplace transform, as we know that the Laplace transform of f of t, okay, it is represented by f of s. So that's why in this particular case, l of f at is equal to 1 divided by a. The constant will be in denominator, and the this a again in the denominator. So let us prove this first. Okay, so we know that the Laplace transform of f of at is equal to 0 to infinity e to the power minus st f of at dt. All right, now let us suppose that at is equal to r, at equal to r, then we will get at if we take the derivative on the both side, we will get dt is equal to dr divided by a, being as a is constant. So this implies that from this we can also write t is equal to r divided by a. So now put the values. Actually we have changed the variable t into the r, so that's why e to the power minus st, in place of t we have to put the value r divided by a. And this f of t, this f of f of at means f of, in place of at we can write r, f of r, and in place of dt we can write dr by a. So 1 by a can be taken outside as its value is constant, so 0 to infinity e to the power minus sr f of r dr. So okay, so by in doing so now what we get, actually we get that this is the 1 divided by a, 1 divided by a, and f of s. Okay. So here if we look carefully, we have replaced this s by a, s small s by a, by the capital S, so we get e to the power minus sr f of r dr. Okay. And if we look at to this formula, this is exactly coincide with the Laplace transform formula, so that's why we get 1 divided by a, 1 by a, and this one is 0 to infinity 0 to infinity e to the power minus sr f of r dr means f of s. This is the Laplace transform. Okay. So but as this s is equal to s by a, so we get 1 divided by a f of s by a. So we can write in this way. We have proved this part also. Now let us discuss another property, and this one is the first shifting property. Actually, first shifting property, this is the also very important property in case of the Laplace transform. So this, according to this property, if f of s is the Fourier transform, then the Laplace transform of e to the power at f of t should be equal to the Laplace transform of f of s minus a. Okay. So let us start from the right hand side first. Fourier transform of s minus a will be equal to, by applying the formula, we would have 0 to infinity so here we will have the Fourier transform of s minus a should be is equal to this one, e to the power minus st. So in this case s means s minus a and f of t dt. So we now multiply this one, e to the power minus st and minus plus at f of t dt. So now let us break down this one. So we will get we will get what we will get that e to the power e to the power minus st e to the power at f of t. So this is, if we consider this whole e to the power at f of t by just one function, then it is quite similar to the Laplace transform formula, so which is 0 to infinity e to the power minus st f of t dt. So that's why in this case this should be equal to the Laplace transform of e to the power at f of t. So this is the another method. This from this method also we can proceed. As we have in the left hand side, 0 Laplace transform of e to the power at f of t using the formula, and in the formula e to the power minus st, and the function is e to the power at f of t dt. So after multiplication, and we will have this one, this one e to the power minus s minus a t and f of t dt. So now let us represent s minus a by u, then it should be quite similar. It is similar to the Laplace transform of the u. It's then again, as we have replaced u by s minus a, we can just write a Laplace transform of the s minus a. So it is not necessary to go through both the methods. One method could be sufficient. Okay, now let us discuss the second shifting property, second shifting theorem. So it states that, if Laplace transform of f of t is f of s, and g of t means f t minus a for t greater than a, and for the value of t lies between 0 to a, its value should be 0. Then and the Laplace transform of g of t should be e to the power minus as f of s. So to prove this theorem, let us start from the Laplace transform of g of t. We need to prove this one, and Laplace transform of g of t is equal to 0 to infinity to the power minus st gt. Okay, this is the formula, no worries on that. And now we can, what actually we can do, we can just integrate this from 0 to start from 0 to a, and then a to infinity. So the value ranging from 0 to a, and then a to then value of t should be greater than a. So that's why first break down this integration 0 to infinity to the two parts. One is 0 to a, and another one is the a to infinity. So that's why we get a 0 to infinity, 0 to a, 0 to a e to the power st gt, and this one. But as we have given that the value of gt is equal to 0 for the range 0 to a, when the value of t ranges from 0 to a, it means that in the first integral, this the value of gt going to be 0, because we have given that for the value of t lies between 0 to a, the value of gt should be 0. So that's why we can write 0 over here, and the first term will be dismissed, or we can say, and in the next term, in the second term, we can actually write, in place of gt, we can actually write ft minus a, because the value of t in this case is greater than a. Okay, the value of a is t is greater than a. That's why for this range, for this integration limit a to infinity, the value of t is greater than a. So that's why I have replaced this value gt by what, f of t minus a and dt. So now again, using t minus a is equal to r, let's suppose that t minus a is equal to r, then by integration dt is equal to dr, because the a is constant. So and then from t is equal to r plus a, from this one t minus a is equal to r, then we get t is equal to r plus a. Then just to convert this integral which is in t to the r. Okay, so there cannot be there should not be any change in the integration limit, and e to the power minus s, in place of t we can write r plus a, and f of r. Okay, because t minus a is equal to r and dr, and in place of dt we have dr. So that's why it reduces to this form. E to the power minus sa can be taken out from the integration, because this value is constant. So 0 to infinity e to the power minus sr f of r dr. So if we and this is exactly the formula of the Fourier transform. 0 to infinity e to the power minus sr f of r dr means this is the formula for the Fourier transform. So that's why we get Laplace transform of gt is equal to e to the power minus as and f of s, which is the required relation. So thank you very much.